Next up, we have Kira Gardner, senior scientist at the Anthropocene Institute and former head of the CITRIS Foundry. She will lead a conversation with Teija Mortvedt from Tesla and Susan Babinec from the Argonne National Laboratory on two approaches to energy storage. Kira.
Hi, thanks, Camille, so much. Welcome to Two Perspectives on Storage discussion today. I'm going to do a brief intro for our speakers so you have a better framing for their background, and then I'll launch into a couple questions for them. Teija Mortvedt is a chemical process engineer with the Tesla Materials manufacturing team. They're working on internal battery recycling systems design. Her focus is on integrating high-value materials from end-of-life products back into the original supply chains. During her graduate work at Rochester Institute of Technology, Mortvedt focused on scrap material recycling, making strategic recommendations to Gardner for process improvements to be made for their steel scrap yards, and implementing sensor-based sorting technology to improve sorting and yields. Her work has consistently been at the intersection of sustainability and materials and industrial manufacturing, with a passion for thinking about full circle sustainable product life cycles. And she obtained her master's degree at RIT in sustainable engineering with a focus on industrial systems and materials, and her bachelor's from Scripps College. Susan Babinec leads a comprehensive strategy that expands the U.S. Department of Energy, the DOE's vision for a future electric grid that includes a range of optimized energy storage capabilities. Babinec previously has served 6 years as the senior commercialization advisor for both transportation and grid energy storage.
昨天那个 Symposium 继续听啊。
at the Advanced Project Research Agency and
结束了。
ARPA-E. If anybody has their sound on, please mute. Thank you. Prior to ARPA-E, she has led several research groups as the technical director of A123 Systems in Ann Arbor, Michigan. And Babinec had spent the first 2 decades of her career at Dow Chemical Corp, where she was awarded the Inventor of the Year award, was senior advisor to Venture Capital Group, and was the company's first woman corporate fellow. She's also the co-inventor of low-cost display technology that was spun out as a venture-funded startup, has more than 45 patents, and has co-authored dozens of journal articles and book chapters. With our two fantastic guests today, I'd love to start with you first, Sue. If we can get our speakers up on this spotlighted, thank you. I'd love to ask the question of, in the last year, venture capital has put more than $18 billion globally into startups focused on technology to electrify transportation. That's a lot of activity. Considering your really broad perspective and your experience, why this flurry of activity in the battery sector, and why do we need batteries? Can you help our audience understand what might be important about storage for the clean energy transition? Pass that to you, Sue.
Hello, everyone. There we go. I'm in my office, which is actually quite messy, but you don't know that. So the question, as I heard it, is there's a lot of activity going on. There's 2 parts of the question. There's a lot of activity that's going on right now. What's up? Why now? And then why do we need batteries? Okay, so the first one is, yes, that is a lot of activity. That is a lot of money. And the reason that there's a lot of money right now is because there is a real market and things are happening. So if you look over the last, let's say 30 years or so, going way back, there was work in batteries for mobility and solar and wind. These things were going on for years and years and years. And then finally, the technology came to the point where it's good enough for mass adoption and the cost is okay. And so there's a ramp up in the market. So the technologies we have now are good enough. They need to be better, and the market has appeared. And so there's going to be tremendous market growth, and that's why there is investment right now. And so actually, even though that number seems high, 18 billion, compared to the trillions and trillions of dollars that will be spent, that number pales in comparison. So they're financial people and they're doing their parts. So that's why there's investment now. The second question is, why do we need batteries right now, and how important are they to the clean energy transition? Well, clean energy means we're going to get rid of CO2. There's many ways in which CO2 is produced. In the very largest perspective, 2 very important ones, which are major CO2 criminals are transportation, and the other one is the generation of electricity. Both of those are being electrified right now, and the key technology for that is batteries. So if you're going to have an electric car, you need to have a battery pack. And so there's tremendous growth. Those battery packs are going on right now, and that is taking off like mad. Climate change has really accelerated what was already going to be a rapid adoption. So you need batteries for electric vehicles. The other one, though, is for power generation. When you turn your light on in your home or wherever it is, you really don't often think about where's that power coming from. In the old days, it was coming from carbon-based fuels, natural gas, coal, or oil. And in the future, it's coming from renewables, solar and wind. Those are the lowest cost. They don't make CO2, but they're intermittent. And since you need power continuously, the solution for that is batteries. And so it's the key enabling technologies for green electricity.
Thanks, Sue. I love how you focused in on the two kind of biggest culprits. Energy production and transportation transportation sector. Kind of thinking more broadly about how do these innovations actually get to market, right? Like you said, it's not going to, I think our previous speaker had said, you're not going to make an impact until that's actually out in the world. Can you talk a bit about the role that agencies like ARPA-E have in scaling from lab to commercial product?
Yes. So first of all, since everyone, I talk to battery people, so it's nice to not talk to battery people. I told myself one of the things I was going to start with when I was asked this question was to just explain to people that making a good battery is actually a very, very difficult thing to do. Okay, so we're used to the world of integrated circuits and chips and big fab lines, and we're thinking about that. That is one level of complexity. I'm telling you that a battery is as difficult or more difficult than an integrated circuit. Okay, there's just more moving parts, more components by a factor of 10. So it's very difficult to actually pull it off. But as I said a moment ago, we need new technologies, and the government funds those. And when I was at ARPA-E, we had the privilege of working with very, very talented people who started with a brand new idea and they wanted to take it to market. And when I was there, we did an actual study that said, if you are like the smartest cream of the crop that you could possibly be, you are so dedicated, you work very, very hard, and you have, the market is there, but just the natural course of what it takes to bring things to market is it takes at least 8 years, if you're really, really good and everything goes well, to start doing piloting, okay? So that's like a really important number. Now, if you think about the United States system, where does technology come from? Well, the government seeds very early stage research, and then very often if you have a spin out, you go and you get venture capital funding. The venture capital funding horizon is not going to last if they don't do 8 years, okay? They have a fund that lasts 10 years. They get in somewhere around 4 years into their fund. They want out in 5 to 6 years. So the problem that we've had in this country is that the natural progression of what it takes to get a battery, a new technology into the market and start generating reliable revenue does not match up with the funding mechanisms we have, which is venture capital. And so we really don't need to be mad at venture capital because that's what they do. We need to look to alternative sources. And what's happened is in the last 3 to 4 years, the government has really stepped up and started providing more programs to help companies move forward. Specifically, there's a lot of activity going on in the energy storage area, and then also ARPA-E, my old organization that I used to work for. They actually have new programs that are meant to take technologies when it's just beginning to pilot and hold on to them and fund them a little bit longer so then they can generate revenue. So it takes a long time, and there's a problem with the ecosystem the way it's been constructed.
Yeah, that misalignment. So trying to fill that gap and match those timings a little bit better. That makes a lot of sense.
Exactly.
Thank you, Susan. We'll come back to you for a question at the end, but I want to jump into Teija's experience actually kind of building the battery. People, I think, like you described, the challenges of the complexity of designing that. Teija, if you jump in here and help our audience understand how our batteries actually manufactured, what kind of considerations are taken into account. Maybe we can just stick with the EV battery since that's such a huge sector right now for the market.
Sure, and apologies, I had my video on, but it short-circuited my phone and my computer camera's not working. So, but at least my voice is here. But yeah, I mean, so batteries are manufactured, initially we take the raw materials. Nickel, cobalt, lithium are kind of hot topics. Right now, everybody is very aware of the short supply in all of these high value battery materials. So those are all refined, processed into battery grade, and then manufactured into individual cells. Those can be pouch, prismatic, or cylindrical. And here at Tesla, we use mostly cylindrical cells, but we're branching out into using a few different types in all of our battery products at the moment. And those are then, each individual cell is integrated into a larger module. So a module can have anywhere from a few hundred to thousands of these individual batteries. And, these batteries are, super important for making sure that the car runs well and efficiently. It's kind of like the powerhouse of our vehicles. Without the battery, you don't really have anything. And the most important factors in designing a really high quality battery for manufacturing, making really quality product and super simply. And luckily, if you do both of those things, a lot of other things follow, such as cost, safety, and sustainability. I would say right now, we're really focused on building quality products. The entire EV industry is, just to make sure that it all catches on and we get good implementation, so that this industry continues to thrive into the future. And sustainability, unfortunately, isn't quite as high up on the rung, but we're getting there and making improvements all the time, as comes with kind of all product design.
Could you just expand a little bit on what does a quality product mean from a battery designer's perspective?
Sure. I would say, so a lot of people focus on the individual cell quality. I would say from that perspective, safety is a really big thing in cars. You don't want a vehicle battery catching fire. And then energy density is, I would say, our next most important factor. Trying to get the most energy in the smallest form factor possible, so that you can minimize all materials usage in manufacturing. That drives down cost, that drives down your environmental impact. So those, I would say, are kind of the two big things.
Thank you. So thinking about that kind of, complicated form factor that batteries can take, all those considerations, size, energy density, chemistry. Is it right to assume, that building into the design and manufacturing an eye for end of life recycling isn't particularly straightforward? Could you talk a bit about how would you think about sustainability? How do you think about that life cycle perspective in battery design?
Sure. I would say not just batteries, but if we think about our entire product system, all of the technology that everyone uses in all of their day-to-day life, right? Do we want that technology use to continue? Yes. Do we want to take care of the planet while we do that? We also do. So we really need to try to get to a place where we've put so much throughout recent history, so much time and energy into the design of all of these technologies, and then also the manufacturing of them, really incredible precision manufacturing, that we need to put some additional fraction of that energy investment into managing these products at end of life. So that can include anything in the product life cycle, from upfront design, thinking about end of life, But I am thinking specifically about, you put so much detail into designing the manufacturing systems of battery. Let's try to put a small amount of equal detail into the recycling systems for that battery. Let's automate them, let's make them improved, let's add improved technologies to make sorting more efficient. Any additional work that can be done on that level will improve this full system loop. And so for batteries, how we do that and improve the total recycling system, again, like I said, from the manufacturing side, you can make a battery more easy to disassemble, design it with, say, more homogeneous plastics mixture so that you don't have a ton of different plastics, so that when you go to recycle, they can all be recovered. In terms of reclamation of the battery, you want to make sure that chemistry is indicated, because that's super important. That's, the second, I would say, like, besides being able to disassemble, chemistry then is the most important item in terms of actually recovering the value from all of those products at the end of life.
What's inside your actual battery.
Right. And yeah, none of this is straightforward at all. And there are a ton of different pieces to the puzzle. But the main takeaway is that if you put a little bit of work in on the technology front to improve recycling, it goes a long way, and you do see a lot of additional improvements.
Fantastic, thank you. I'm going to jump back to Sue and kind of dig into the idea of decarbonizing different sectors, right, that are responsible for those large emissions. In terms of electricity, energy production, right, on the grid, we have the need for charging our electric vehicle batteries, this kind of grid scale storage to support renewables like solar and winds. Getting these technologies deployed seems like it's our #1 priority. Could you help us understand what are some of the barriers or challenges to actually getting these technologies out in the world in a usable way?
Sure. That's like a really important question, because we all think that it's like game over, the thing works, but it's like, no, there's a whole new miniseries, right? And so here's a couple of them alluded to just a minute ago. One of that is like front and center right now is actually the supply chain of the raw materials that are feeding into the making of the cells. So the dominant, I thought I heard something. The dominant chemistry for right now and for the next 5 years is lithium ion.
Is this just my internet or is it Sue's? Can you say that again, Sue? I lost your connection for a second.
Oh, I'm so sorry. Okay, can you hear me? Is it better?
You're good.
Yeah,
You said something about the ag sector, and that was the last thing I heard.
No. I was going to say the supply chain is a very big problem right now. So what I was saying is that we tend to think it's like happiness once you get the technology to work, but the manufacturing of it is a huge deal. And part of that is because the ramp up is so tremendous. And there are two sort of categories. Are there enough of the raw materials available? And then do we have the actual production capacity? And right now we're in trouble on all these fronts. Cobalt is a material which is in the cathode. That is a material which is not naturally abundant. It's in certain locations. It's key to the cathode, and the government of China has basically gone out 5 to 10 years ago, and they bought up all the natural resources for cobalt. So supply of cobalt is a problem. Here at Argonne National Lab, we're devising cathodes that don't have it. So supply of cobalt is another one. Nickel is less precious. It's more uniformly distributed, but it's in certain geopolitical hotspots right now. And the nickel supply, with the present unrest that we have over in Europe, that actually was shut down. And so there's going to be a short-term problem there. Long-term, we have to work on production of it. And then lithium, which is key to the whole thing. It turns out there are lithium resources out there, but there is not the production capacity for it. So we are also in a lithium shortage. So the first problem is getting the raw materials. People are working on it. We're going to rethink the way we do things, but that's a problem right here and now. Okay. A second very important problem is getting good people. This industry has ramped up so quickly. We don't have qualified people. The government, the United States, the Department of Energy, and the Electrochem Society, we have programs to get people to help like actually populate these plants and do the work. Another one for EV is very important. A critical gap that we have right now is to have sufficient charging stations, just the way you have gas stations everywhere you go. We need to have charging stations in the United States. There was just something like 15 or 20 billion dollars was put out into the infrastructure bill to build charging stations. So the situation we have right here is that that's a limitation. In the future, 5 years from now, it will not be a limitation, but that is a here and now very important problem that we have. And it's especially egregious for folks who live in very dense urban areas or in apartments, because if you have a house, you can put a charger in your house. There's a lot of people who want these electric cars who just don't have access to it because they live in apartments or condominiums, okay, in dense situations. So that's another one. Now the grid and putting renewables on the grid has a unique problem there. And there is the folks that are going to be purchasing the energy storage to go either with their solar asset or with their wind, they are not that familiar with the technology. If you compare grid to automotive, the OEMs and the transportation world and the Department of Energy, they worked hand in hand for like 30 years to develop these car batteries. And when they're ready to go, everybody's familiar and they're all they understand how it works for these investments. When it comes to renewables and the grid, the primary customers are large utilities and they are not well versed in what this technology is. They don't have a cost structure that allows them to do research. So there's a gap, which is a lack of enthusiasm because they don't know, they're not really familiar with this, okay? That's a big problem. And we're working with the utilities to help close that gap.
Yeah, thank you. That's a pretty, I think, well-framed showcase of a lot of the very specific issues that deploying these in different sectors is going to have. I think we're at time now. I know I'd love to give Teija 1 second to say a thought around the idea of opportunities for new students, talent, and workforce. Teija, could you just say one sentence on why students in the audience might consider this a career for them?
Sure, really quick. There is a ton of stuff to do on all fronts. You could work in mining to try to get more of these materials. You could work on sustainable mining. You could work on policy and regulation, design, a ton of stuff, a ton of gaps, so many opportunities. So a lot of hope for the future.
Fantastic. Thank you both so much. I really appreciate your perspectives today, and I'll hand it back to you, Camille.
Super.
Thank you.
Thank you. Thanks so much, Kira, Teija, and Susan for helping us to think through energy storage challenges, the research to implementation gaps, and how we're going to continue to power our lifestyles with more care for the planet. I also appreciate the suggestions around workforce development and getting engaged with any number of these problems as a career path. That's really helpful to the students in the audience and any others who might be thinking about the role of their careers and their purpose for what they want to bring to it.